In this video, we'll talk about adversarial search for game AI, and we'll discuss one method for speeding up the computation of the search tree. That method is called alpha-beta pruning. You ready? Let's go. In order to understand alpha-beta pruning, we must first remind ourselves about a popular recursive adversarial search algorithm called Minimax. Here's the basic idea. If we are developing an AI to play a game, we can look at the state of the game at any given time. I'm depicting that here with a labeled circle, but a more concrete representation might be a tic-tac-toe diagram with X's and O's, or a chessboard with pieces that have been moved around by the players. We call these states nodes, and at each node, our AI can make one of several decisions. Those decisions alter the state of the game, resulting in more nodes. This process gets repeated over and over, which is why we say the algorithm is recursive. Eventually, the game tree reaches a state beyond which it cannot expand. We call these states terminal nodes, and each terminal node contains a value that we call the utility. Utility measures the usefulness or desirability of that particular game state to our AI player. For tic-tac-toe, we may assign states in which our AI wins a utility of 1, and nodes in which our AI loses a utility of -1. If there is a tie, perhaps we assign 0 utility to that node. For this example, I'm using a wider variety of utility values, simply to make the algorithm a bit more interesting. Keep in mind that the absolute magnitudes of utility values are not as important as the relative magnitudes with respect to other nodes. The goal of Minimax is to search for the best possible decision at a given node, then the best possible decision at the resulting node, and so forth until we reach a terminal node with hopefully maximum utility. So why do we call it adversarial? Well, looking at this game tree, it appears the maximum utility for our AI player is 14, which is achieved by taking moves A3 followed by D1. But wait, that's not how games typically work, at least games involving more than one player. Let's assume here that this is a 2-player game. At the top node, perhaps it is the AI's turn, so we want to maximize the utility for our player. But as soon as we make a decision, it is now the turn of our opponent, or adversary, if you will. The goal from our opponent's perspective is to minimize the utility of this tree. So if we take move A1, resulting in state B, then our opponent should take move B1, because B1 has the lowest utility of the 3 options at that node, and that benefits our opponent the most. If we take move A2, then our opponent takes C1 with the utility of 2, and if we take move A3, then our opponent will take D3 with the utility of 2. Assuming our opponent plays perfectly, the utility of the states we can move to from node A are 3, 2, and 2, respectively. Since we want to maximize that utility, we take A1, then our opponent takes B1, and the overall utility is 3. Note that this is significantly lower than the actual maximum utility here, but that is to be expected. We don't want our opponent to hand us the game, do we? So, adversarial search, and more specifically Minimax, involves alternating between competing objectives in the game tree. For simple games like tic-tac-toe, we can compute the entire search tree at each move, because the tree has a maximum depth of 9, which is the highest possible number of moves in a game. This yields an upper bound of 9 factorial unique game paths through the tree, or roughly 350,000. Even so, I'm only showing part of the tree here, starting in the middle of a game. For this game, terminal nodes include victories for our AI, who is playing the X's, some losses, and a handful of ties. For more complex games, like Connect 4, Checkers, Chess, Othello, and Go, among others, it may not be practical to generate the entire tree. This is where pruning comes into play. To demonstrate how pruning works, let's look back at the earlier example and search through the tree as the Minimax algorithm would. Starting at node A, assume it is our AI's turn and we want to pick the decision that maximizes utility. We start searching to the left at node B, at which point our opponent is trying to minimize utility. Each of the 3 decisions at node B result in terminal nodes, so we assume our opponent will take the option leading to the minimum utility, which is 3 here. Backing up the tree to node A, we begin exploring our second available decision that leads to node C. As we begin searching the possible options for our opponent to take, we hit a terminal node with utility equal to 2. Now let's pause for a moment and think about the implications of this finding on our overall minimax search. At the highest level, the AI is trying to pick the decision that has the maximum utility, which right now involves 3, and whatever utility comes as a result of choosing decision A2. But at node C, our opponent will choose the decision leading to the minimum utility, which we know involves 2, followed by all of the unexplored utilities. Because our opponent is picking the minimum value, we now know the utility at node C will be at most 2. But if that's true, then our AI doesn't need to explore from node C anymore, because choosing move A1 that leads to node B will result in the higher utility of 3. So we prune the rest of the tree at C, label the utility to be less than or equal to 2, and move on with the search. As we explore the third available decision from node A, leading to node D, we end up at a terminal node off of D with a utility of 14. Let's pause again. Should we continue searching this branch of the tree, or prune it as before? Pause the video to answer this for yourself. Did you figure it out? It turns out we should not prune the tree here, because if our opponent's best option is to choose a path that leads to a utility of 14, then move A3 will be preferable for our AI over move A1. But it is possible that our opponent will have better options, so we keep exploring. And it is a good thing we did, because it turns out the best option for our opponent at node D is D3 with a utility of 2. Therefore, the best move for the AI at node A is to take move A1 with a utility of 3. In this example, we eliminated the need to compute 2 nodes, a modest gain, especially for an already small search tree. However, this same approach can yield much bigger gains for other problems. Can you think of the maximum number of nodes that can be pruned relative to the size of the tree? Take a minute to think about that. It turns out that pruning can reduce node computation by up to 50%. I'll leave it to you as an exercise to think about how that might be achievable. One important factor that determines the benefit of pruning is the order in which moves are searched. You may have noticed in this example that pruning 2 nodes from C depended on the fact that the terminal node with utility 2 was explored before the nodes of 4 and 6. Furthermore, searching node B first also played an important role, because that is where we got the value of 3 with which to measure other utilities against. If that seems confusing, let's try the same game tree, but with the nodes switched around a bit. Here, I've swapped the order BCD to DCB, and also reversed the order of children from node C. I should note that you could have kept the tree as before, and simply changed the direction of the search as well. Either method demonstrates the same principle. So, let's build the tree using minimax with pruning. We start at node A, then move left to node D, then one by one evaluate the terminal nodes at D. The minimum utility of 14, 5, and 2 equals 2, so that becomes the utility at D, and we move back up the tree to A. Next, we start searching node C. The first terminal node that we reach has a utility of 6. Recall that this is the point at which we previously pruned the tree. However, we cannot do that here because a utility of 6 would be chosen at node A over the utility of 2 at D, assuming 6 is the best choice for our opponent at C. We therefore must continue the search to find that the minimum utility at C is also 2. Continuing on to node B, we also must search all terminal nodes because none of them has utility less than the best option for our AI at node A. Even though the nodes of the tree are identical to before, we end up with 0 pruning here, based on the order in which moves were generated. The takeaway here is that order matters. The best strategy is to prioritize moves that seem most promising first. So moves for the max player that you think might lead to high utility, and moves for the min player that might lead to low utility. And this is easier said than done. Indeed, if we knew which moves were guaranteed to be most promising, we wouldn't even need Minimax in the first place. Just use that information as the AI. Okay, we've seen pruning work conceptually, but where do the alpha and beta come into play? Let's formalize our definitions a bit more. We can define a variable alpha that represents the best utility found along a path for the max player, and a variable beta that represents the best utility found along a path for the min player. The wording can be tricky here because best for the max player means highest, whereas best for the min player means lowest. Every node will have its own alpha and beta, and these values may update when new nodes are explored. The key principle of alpha-beta pruning is to stop searching along a path whenever the utility of the current node is worse than alpha or beta, depending on which player we are worried about at the time. This may make more sense with an example. Let's search a new game tree from scratch. We initialize the root node with the worst possible values for alpha and beta, which are -infinity and +infinity, respectively. Make sure it makes sense why the signs are this way. As we search new nodes to the left, copy the alpha and beta values from the parent node along the path. As soon as we reach a terminal node, we compare the utility with either alpha or beta. Since the parent node here corresponds to the max player, alpha is the variable we are concerned with. -2 is greater than -infinity, so update alpha accordingly. The next terminal node has a utility of 3, which is greater than -2, so update alpha again. At this point, there are no more nodes to explore along this path, so the utility of the node is set to the maximum of -2 and 3, which is 3. Moving up the tree to the parent node for the min player, we now have the utility of one of its children. We should compare this value to beta, which represents the best utility for the min player so far. 3 is less than +infinity, so we update beta to 3. Let's continue searching until we find another terminal node. At this terminal node, the utility is 4. Now that we're focused on the max player again, alpha, which was -infinity, gets reset to 4. Here's the important part. Because alpha is greater than beta for this node, we can prune the tree here. Why is that? We know that the max player will make a decision with a utility of at least 4. But the min player already has a better or lower option at the node up the tree of 3. So we will never take this path in the tree and can move on with the search. As we return to the root, notice that we updated alpha because of the utility going down the tree to the left. As we explore the tree to the right, the initial alpha value of nodes is no longer -infinity, but 3. We search until we hit a terminal node. -5 is not greater than 3, so we don't update alpha, and neither is 1 greater than 3. But this doesn't affect our computation of the utility at this node for the max player. The maximum of -5 and 1 is still 1. We propagate that up 1 level to the min player. Now, the utility of 1 is less than the current beta value of +infinity, so we update beta accordingly. Once again, we have reached a critical juncture. Notice that beta is now less than alpha at this node. This means that even though the min player will choose at most a path with utility equal to 1, the max player already has a better option in some other path with utility of 3, so we can prune the entire remainder of the tree emanating from this node. For this problem, we're done, and the path that would be taken goes left, left, then right with a final utility of 3. Speaking of utility, I hope this video was useful in helping you understand how pruning can improve Minimax search for AI in games. The next step is to translate these ideas into actual code. I'll let you get a head start on that on your own. Any questions?